Back to your book, Astrophysics for People in a Hurry. 14 billion years ago, the universe started, you say. How do we know? How do we know that?
So the way knowledge is acquired scientifically is you have an idea and you propose an experiment to test the idea. And then if it's an expensive experiment, you probably don't have the money to do it in your garage. So now you propose to get funding from sources. Typically, if it's pure research, it'll be a government source. The National Science Foundation, NASA has a research arm. If you're in the other fields like biology, human physiology, you might be getting a grant from the National Institutes of Health. And so you have this idea, you build an experiment, and you test it. And if the results of that experiment match your expectations, then the foundation of your idea gains some currency in the conversations you might have at the scientific coffee lounges, at workshops, or in the journals. Then you're a competitor of mine, and you say, you know, I never liked you. I have a different, scientists are humans, we're people too, right? So, and I think you're wrong. And here's the experiment I'm going to build to show that you're wrong. So then you build an experiment, and then you get a result that kind of matches my result. Well, that's interesting, because you had no intent of matching me. You don't even like me. But now the results match, and someone else does it. You'll always have some outliers, just because of the experimental uncertainties that exist in all experiments. There'll always be some outliers. But when there's a general lean towards a truth, an emergent truth, you look back and you say, oh, okay, all of these experiments point to approximately the same result. And you have these few outliers here. So now we come to recognize that this is the new truth, the new objectively established truth. And that's what science does. It is the most effective way we have ever devised as a species, as a culture, in decoding what is and what is not true about the natural world. Nothing rivals it at all. And so once we've done this, then I say, here is how the world works. Then we go on to the next problem. And this is a celebrated thing. I mean, it's what got us relativity and quantum physics and gravity, and it empowered the entire Industrial Revolution. You couldn't have these machines. What is a machine? It's something that converts energy that lives as one form into energy that's useful to us in another form. So what is a car? It takes chemical energy and gas and turns it into energy of motion, kinetic energy, of your car. And that requires machines to do that. All this came out of the Industrial Revolution. Before the Industrial Revolution, there were no machines such as this. They had what we call simple machines. A lever and a pulley. Those don't require high technology. Technically, in the world of physics, those are called machines. Okay, a lever, a pulley, an inclined plane. And what they do is they make your job a little easier. So it's simple. So watch how this works. So I have this ledge, and I have a very heavy thing, and I want to lift it up to that ledge. Well, I'm not strong enough to do that. But if I make a ramp, then I can just lift it up little bits at a time. Now, the distance over which I have to lift it is longer, but it takes this height and spreads that out over time so that it makes it easier for me to complete the task. The same amount of total energy is exerted, but the rate at which I expend that energy is different. And that's what simple machines have always done for us. And modern machines basically empower all of civilization.
First 10 seconds of the universe, what happened?
Well, so there's some busy moments back. Oh, sorry, I didn't really focus in on your question about how do we know it's 14 billion years. So here's what we do. We look up in the universe, and we say, okay, we see galaxies. Hubble discovered that these fuzzy things in the night sky are entire galaxies, such as our Milky Way. Major discovery in 1926. And then in 1929, he discovers that these fuzzy things that we now identify as whole galaxies are hurtling away from one another. And this is the first evidence that the universe is expanding. So people don't just think this up. Oh, it must be, no. It was an observation. And then we looked to see if it fit Einstein's general theory of relativity, and it did. General theory of relativity is the modern understanding of gravity. And if anything's happening in the universe, it's going to involve gravity. So you check to see if it works with his equations. It does. And so that means we didn't have to reinvent a theory of the universe because it worked. And so then we say, all right, if the universe is getting bigger, if the universe is bigger today than it was yesterday, and that must mean it was bigger yesterday than it was the day before, and then the day before, and then the day before. So what happens if we just turn the clock back? When you do this, because you see how fast we're expanding, just reverse that. You can do it on a pen and paper, on the back of an envelope. Just calculate what happens if you reverse this rate of expansion. And the whole known universe is in the same place at the same time 14 billion years ago. That is the origin of the idea of the Big Bang.
First 10 seconds.
First 10 seconds. So everything we know about matter that is compressed and under pressure tells us that the temperature will rise. And the simplest example of this is if you ride a bicycle and your tire gets a little flat, so you pump, a hand pump, you pump air into the bicycle tire. And then you feel the valve when you're done. It's hot. You are compressing air through it, okay? And so that's just as an example. So it's related. It's not exactly the same thing, but it's related thermodynamically. The science of the movement of energy from one medium to another. It's called thermodynamics. So as the universe gets smaller and smaller, it actually would have been hotter in the past than it is in the present. And so now you keep, because the universe actually now has a temperature, you can measure it. Got measured in the 1960s. Very cool. You look in every direction and you see the heat signature left over after the 14 billion years. And so now you go back in time and you say, okay, the universe was hotter and hotter and hotter and hotter and hotter. How much hotter would it have been 14 billion years ago when the universe was this big? And you get a stupendously high temperature. And now you ask, what is the behavior of matter and energy under those temperatures? So now you turn to the particle accelerators that slam particles together under high pressure, high energy, high temperature. So you start approximating the conditions of the early universe. Well, is that what an atom does? Is that what a nucleus does? Is that what happens? So now you take knowledge gleaned from modern atomic physics and particle physics, and you apply it to what's going on in the first few moments of the universe when it was hot, small, and dense. And that gives you a pathway in, a pathway of insights into what was going on there. You know what we find? That you have an era where all particles are formed, the basic foundational particles that everything else is comprised of. We have light in the form of photons. We have quarks that make up protons and neutrons. We've all heard of protons and neutrons. They're made of something else. They're made of what we call quarks. And as far as we know, quarks are fundamental, as far as we know so far. And also electrons. And they all have antimatter counterparts. An electron has an antimatter. It's called the positron. It's a very cool name, actually. Positron. Something that science fiction people rapidly picked up on. Just to be clear, we invented antimatter and discovered it. That was not a science fiction invention. Although it works great in science fiction storytelling, it happened in the real universe first. So now you bring your insights to those first few moments of the universe and say, what must have happened then, given what we know goes on in our particle accelerators? And it will tell you, at the rate we were expanding, at those temperatures, you would be making hydrogen as the predominant atom in the universe. It's the simplest atom. It has only one proton in the nucleus. You make this much hydrogen. You make this much helium. That has 2 protons in the nucleus. You'll make trace amount of lithium. That's the 3rd element on the periodic table of elements we remember from chemistry class. And nothing else. We will be a universe born with hydrogen and helium and barely any lithium. Wait a minute. And you say, if that's so, it would mean that the very oldest stars we can find, ones born closest to the Big Bang, that would still be alive today, would be comprised of only hydrogen and helium. That is exactly what we measure. The very oldest stars have the least amount of heavier elements, which we know this from the mid-20th century, from calculations enabled by the nuclear research from the Manhattan Project and the atomic bomb, because we're calculating what atoms do. We know that after that time, stars are born, pure hydrogen and helium. They manufacture heavy elements in their core. Then some of them explode, scattering this enrichment to gas clouds that have yet to form stars. Now they form a next generation of stars that have a little bit of extra enrichment. They'll make even more enrichment, explode, and then carry that extra enrichment to the next generation. And this continues through. Our solar system, was born 4.5 billion years ago. So that's more than 9 billion years after the start of the universe. So we've had the benefit of multiple generations of enrichment. So now when our protocloud collapsed to make the sun, it had all these other ingredients in it that it used to make planets. Because rocks are not made of hydrogen. They're not made of helium. They're made of silicon and oxygen and aluminum and arsenic, all these other iron, cobalt, nickel, all of that manufactured later is in abundance in very late generation stars that were formed. So the lesson here is, however weird it is to assert that 14 billion years ago the universe was this big, literally this big, and exploded from there. You say, well, you weren't there, how do you know? Okay, you're right, I wasn't there. But if everything we know happens to matter, happened then it accurately predicts things we do measure. That's what gives us the confidence to sit here and describe the first 10 seconds of the universe like we were there.
And it all started with the Big Bang.
Is there a song in there?
Do we know what that Big Bang was?
Do we know what it was?
Yeah.
What we can tell you is that the Big Bang account of the beginning of the universe is a description of what matter and energy was doing from the earliest moments onwards. Now there's a point before which it's a little mysterious to us. It's called the Planck time, named after Max Planck, one of the many fathers of quantum physics. There's a point earlier than which it's kind of the limits of our ability to understand what nature is doing. So we pick it up right after that Planck time. I forgot the Planck time is like 1 trillionth of a second after the Big Bang. No, 1 billion trillion trillionth. Is that right? 15, 12, 24. Yeah, that's about right. 1 million trillion trillionth of a second after whatever was the beginning. Then our physics that we now measure in our labs apply. And then we can talk about what's going on.